Hey class, so I understand that a few of you have been trying problem 41 on the homework and found it a little bit tricky. So I thought I'd go ahead and make a video since it is quite tricky and there's a couple different ways to approach it. I'm going to walk you through the way that I think will be most beneficial. So what we see here is we have a situation where we have some ice that is well below freezing. It's at -15 degrees C, as you can see here. We're told that there's two ice cubes. Each ice cube has a mass of 0.026 kilograms. Then we're placing those in water that's at 21 degrees Celsius, and we have 180 grams or 0.18 kilograms of water. So first we're asked to determine what is the equilibrium temperature. And the challenge here is you can't necessarily just jump into one set equation to figure out the thermal equilibrium temperature. It depends. Will the ice melt? Will some of the water freeze? Is it going to be below the freezing point? Is it going to be at the freezing point? Is it going to be above? Those are all good questions. So to help you think about this and understand, I went ahead and made one of those temperature versus heat graphs that I showed you in class the other day. So what we have is a situation where our ice, which I'm representing with the color purple here, starts down here at -15 degrees C. Okay, and we have water that starts up here at a point of, I think it was 21 degrees C maybe. Anyway, we can double check. Yep, 21 degrees C, okay? So that's our situation. Now what's going to happen is we know that heat is going to flow from the warmer object to the cooler object. So there's going to be a tendency for the water to move down as it gives heat away to the ice, and the ice is going to move up this direction as it gains heat from the water. What we don't know is where we're going to end up. We could end up somewhere in this region where the water freezes. We could end up somewhere in here where some of the ice melts and the water arrives at a temperature of 0. Or we could end up somewhere up here where our ice entirely melts and then we have water. So we don't know. It depends on the quantities and the different specific heats and so on. So what we really have is a situation where there's 3 different segments, right? There's segment 1 here where we're going to have warming ice that's going from -15 up to 0. So that section would end at this location here. We're going to have a section up here where our ice could melt, or our water could freeze, really, depending on which way we go, in here. And then there's a third section up here, which is the section where the water can be cooling down, starting here and ending here. And there's a certain amount of energy that's required to cause each of these transitions, hence the Q, right? And so what we need to do is we need to look at the Q value required for each of those transitions, and then depending on how they relate to one another, that will tell us where we're going to end up. So let me kind of show you what I mean by that. So if we start with energy transition 1, okay? In energy transition 1, we're going to have a Q value. Maybe I'll switch to purple again since that's our ice color. Okay, we're going to have a Q value for that first segment where our ice is warming up that's just going to be equal to the mass of our ice times the specific heat of the ice multiplied by the change in temperature that the ice endures. And in this case, that change in temperature would be going from the -15 up to the 0. Okay, so in this case, if we plugged in the values for my problem here, we'd have 2 ice cubes, each of which had a mass of 0.026 kilograms. And we're multiplying that by the specific heat. I'm going to run out of room, probably. And so our specific heat of ice, which is different than the specific heat of water, keep in mind, is 2,220. And our units are joules per kilogram degrees C. And then we have to multiply that, or I'll scoot over some more. I'll come back to the graph here in a minute. And multiply that by our delta T. And our delta T is our final temperature 0 minus our initial temperature -15 degrees C. So we end up with a delta T of 15, a positive value. So in this case, if we went ahead and calculated that value, what we would find is that the Q for this first energy transition would be a total of 1,732 joules. So that's how much energy the ice would absorb as it warms up to 0. Okay, sounds good. Now let's compare that with energy transition 3, where we have the water cooling down. Okay, see how much energy the water can give up. And then we'll see what, if anything, we need to consider in the middle section. Because we could have, in that middle section, in section 2, you could have ice melting or water freezing depending on what has more energy. Okay, so now we're going to look at the water for Q3. And again, we have mass. Now it's the mass of the water. C, the specific heat of the water, and delta T. All right, for the sake of time, and I trust your abilities, I'm just going to give you my results. So what I found when I calculated the mass of the water times the specific heat of water times the change in temperature going from its starting point of 21 degrees C to 0, we find a negative Q value because it's giving up heat. Its temperature is ending lower than where it started, and I found that it has a Q value of negative 15,823 joules. So what does this mean? What this means is the water has a lot more potential of heat to give up than the ice can absorb. So what we can see, because Q3 has a magnitude much larger than Q1, by the time the ice gets to 0, the water is going to be well above 0, and so it will start melting that ice that's at 0 degrees. So now we have to look at section 2, and as we look at section 2, we need to consider the fact that the ice will now be melting. Okay, so now we have melting ice, so we want to look at how much energy it would take to melt all of the ice. So to melt 100% of the ice, the energy it would take would be equal to the mass, the total mass of the ice that we have. Actually, let me rewrite that. So based on what I had at the beginning, it's really 2 ice cubes that each have the mass of a single ice cube, multiplied by the latent heat of fusion for the ice. That is an F that looked like something weird, so I'll go ahead and rewrite that. So once again, if I plugged in my values, what we would find is that the ice would have to absorb a total of 17,316 joules. Okay, so what we can see here is if we look at our different values, what we observe is that our magnitude of Q3 is larger than Q1. So that means ice is going to melt. That's what that tells us. Okay? So by the time the ice gets to 0 degrees Celsius, before any has melted, the water has cooled down, but definitely has leftover energy. But then if we observe again, what we see is that the magnitude of Q1 plus Q2, the total energy it would take to melt all of the ice, and after heating it up to 0, that is greater than our magnitude of Q3. So what that means is the water cannot give up enough energy to melt all of the ice. So based on that fact alone, we could actually determine what the equilibrium temperature is going to be. What we find is that our equilibrium temperature for this first situation will be equal to 0 degrees Celsius in my case. What? You say? That seems way too simple, right? Or way too confusing, one or the other. But again, it's all about the energy transition. So we don't have enough energy to melt all of the ice, but we do have enough energy to get the ice up to 0, and so therefore some amount of the ice is going to melt. And if you wanted, you could calculate exactly the number of grams of ice that melt and the number of grams of ice that remain unmelted. But since we're not asked to do that, we don't have to worry. Okay, that sounds good. Now we have to consider question 2. So in question 2 now we say, okay, what happens if there's only one ice cube? And so to do only one ice cube, you have to really redo these calculations. If there's only one ice cube, you have to find a new Q1, you have to find Q3 stays the same, and you have to find a new Q2. Alright, once again, I trust your guys' ability to do that, and so I'll tell you a little bit about what I found. Okay, if I redid this, what I found is for part B here, in this new situation, my Q1 is equal to 866 joules, and my Q2 to melt all of the ice came out equal to 8,658 joules. And so the total energy to get all of the ice melted and right to the 0 degrees Celsius, ready to start heating above 0 degrees Celsius, came out to be equal to 9,524 joules. That's a J. So what we can see here from this is that the heat required to melt all of the ice is less than the amount of energy or heat, not equal to, sorry, is less than the magnitude of our Q3 value. What does that mean? That means that we're going to have an equilibrium temperature that is above 0 degrees. So what we've just discovered from that alone is that our equilibrium temperature in part B is going to be greater than 0, and then we know because where the water started that it's less than 21. Okay? So that's fun, but how do we figure out what that actual equilibrium temperature is? Well, now that we know what happens, we can put all of this together. So I'm actually, at this point, going to switch back to the problem statement where we started so long ago. And so we're looking now at part B here, and what we are going to do is we're going to just consider our energy transfer, right? So we have Q1 plus Q2 plus Q3, and then I'm going to add plus a Q4 equals 0. Now what is Q4, you ask, right? And let's go back to our picture. There's no Q4 drawn on here. What's he talking about, right? That's an age-old question. What Q4 is now the ice water that has melted is now going to be moving up. Since we're ending up somewhere in this circle, this here would be our fourth energy transition. So 1 is getting the ice to 0, 2 is melting the ice, 3, because of how I drew it originally, is the cooling of the water, and then 4 is the heating up of the ice once it has become water. So it's melted and is now a liquid water. Okay? Oh boy howdy, this is a good problem, isn't it? Alright, so let's figure this out. So Q1, that again was our ice melting. So what that's going to look like is the mass of the ice times the specific heat of the ice times the delta T of the ice. So I'm going to actually write this out so we understand what we're looking at. So the delta T of the ice is your ending spot, which is 0. The ice only gets up to 0 and then it turns into water, so we're not going up to the final temperature. 0 minus wherever we started, T initial of the ice, which as we can see up here is just negative 15. Alright, that's Q1. Q2, again, we said was the melting of the ice, so plus the mass of the ice multiplied by the latent heat of fusion for the ice. Again, we decided all of the ice is going to melt, plus, now we got Q3, so that's our water. I'm going to switch my colors to keep organized. So Q3, that's the mass of the water, specific heat of water, times its change in temperature. Its change in temperature is going to be this mysterious final temperature that we're trying to figure out, minus its initial temperature. Temperature of the water initial, which is 21. We know it's going to end up below that, so this term here will be a negative term, right? Then we have plus T4. Now I'm running out of room, so I'm going to write it underneath. Plus T or excuse me, Q4. Now that's the water that came from the ice melting, being warmed up. So we got the mass of the ice. Now we need the specific heat of water because the ice is now in liquid form, being heated up, and it's ending up at some final temperature, which we'll call TF, and it started at 0 degrees Celsius, and that's equal to 0. So now we have an equation where we know the mass of our ice, we know the specific heat of water and of ice, the latent heat of fusion. Everything in here is known. The only thing we do not know is the final temperature of our solution, our equilibrium temperature. So you should be able to algebraically solve and find the correct answer. You know from what we discovered earlier that that final temperature, where'd it go? Oh boy, all kinds of fun stuff here. The final temperature must be somewhere between 0 and 21. So if you don't get that, you made an algebra error. Anyway, long video. I hope that helps a lot, and you guys have a great day.